Okay, so today we are going to talk about electric currents and how electricity moves through wires and how those charges move around. So we have said already that electricity and electric charges are the attractions of protons and electrons to each other. Those positive and negative charges are attracted to each other, and that's what's creating that energy. So an electric current is the movement of electric charges in a single direction through a wire or something that is a conductor. The voltage difference is what causes that electric charge to flow. So it has to flow from something that's high to something that's low. In biology class or any life science class, you learned that water and everything on the earth goes from an area of high concentration to an area of low concentration. Electricity and electric energy are no different. Electric charges are going to follow that same rule of thumb. They're going to go from where there's a lot to where there's not. So an electric current is measured in amperes. I just like the way that sounds. Y'all probably heard of it as amps. That's what most people call it. They're in constant motion in all directions. So electrons don't naturally flow. Electrons are naturally like dropping an entire bag of bouncy balls in a room and just watching them bounce everywhere and go and go and go and go and go. That's what they're going to do. They're going to bounce everywhere. They're going to go in 50 million different directions. So we need a way to contain those electrons and direct those electrons one way or another. What we're going to use is a wire. So a wire is going to contain that electric current. That electric current wants to stay somewhere that's a conductor. It doesn't want to go somewhere that's an insulator. A lot of times wires are going to be wrapped with rubber, electric tape, something like that. You've always, even your iPhone charger, all of that is wire that's wrapped around with an insulator. That insulator is going to keep those electric charges inside the wire. So what happens is those electric charges are still bouncing off the wall and going everywhere, but they can't escape. So as they bounce and zigzag and go everywhere, they're eventually going to move down the wire. If you were to look at a wire, you wouldn't see all these electrons bouncing around. It's on the microscopic level, and it happens so fast that our naked eyes couldn't see it. But that's what's going down. So even though they still move randomly, they bounce off the walls, and they eventually are going to make it down the wire. It's kind of like a ball going downstairs. If you drop the ball on the top of the stairs, it's going to hit the top of the stairs, the bottom of the stairs, the top of the stairs, the bottom of the stairs, the walls maybe, but eventually it's going to make it to the bottom of that stairwell. Same thing happens with an electric current. Now, an electric current isn't going down a hill, but an electric current is going from where there's a lot to where there's not. So it's not going to go back up to an area where there's a lot of people. It's going to keep traveling down to that area where there's not. So the voltage difference. So electrons flow from positive, or electrons flow towards the positive charge. So the electron flow is going one way, and the current we use is going in the other. That's our voltage difference. So that's what gives us 110 volts to 20 volts, something like that. That's what this is going to be. If you put this in full screen view, it has a little area that'll talk to you, and it'll show you the actual flow of the electrons and how it works. A circuit is a closed path that the electric current follows. So it connects it and it makes one big circle. So we use batteries a lot of times to complete a circuit. If you've ever had anything that needs a battery in order to work, when you put that battery in, what you're doing is connecting the circuit. So it's open and you add that battery and it closes it in. The batteries, the wires, and the voltage difference are what allows that current to flow. And it keeps flowing in a circle. Those electrons are trapped. They're going to flow in that circle until you break it. When you break it, it can't flow anymore. And when you reconnect it, it starts flowing again. A lot of times, or most always, that voltage difference is driven by a battery. And we're actually going to get into how batteries work. And in order to show you what that voltage difference is, we use circuits for a lot of things. We use them in our computers. We use circuits. This is a picture of a little diode LED light. We use circuits to light our lights in our house. We use circuits to conduct sound energy. So they're really important in our lives. Without circuits, we wouldn't be able to do most of our daily tasks. I wouldn't be making this video for you right now. So a battery. We said earlier that something has to go from an area of high concentration to low, so where there's a lot of electrons to where there's none. And that's the same thing that drives battery. So it flows down that concentration gradient. A dry cell battery is the battery that's most familiar to you. A dry cell battery is a AA, a AAA, a D, a C. It's what you put in your toys when you were a kid. It's what you put in the remote for your TV now, unless it's an Apple remote. It's what you put in the traditional television remote. So what we have in a dry cell battery is two electrodes. We have a negative end and a positive end. If you've ever installed batteries in something, you know that. They have to go in opposite directions. And inside the battery, there's a paste. And that paste has several chemicals in it. Carbon, manganese, I would have to look that up. That's ammonium chloride. I'm sorry. There was a momentary brain fart there. That paste has all the chemicals in it. That chemical reaction is what's going to drive that concentration gradient. So when it's connected to the circuit, a chemical reaction occurs, and those electrons are transferred. The carbon rod in the center becomes positively charged, and this zinc casing on the outside becomes negatively charged. So you're going to have your positives, or you're going to have a concentration gradient. You have a flow, you have a difference in charges, a positive and a negative. So now we've created a flow of electrons. Once we've created that flow of electrons and electric charges, now we can make a circuit. So we need to connect it to the circuit in order to activate the chemical reactions. When the chemical reactions are activated, those electrons are just going to flow from positive to negative, and they're going to keep, or from negative to positive, and they're just going to keep going around and around and around until you remove it. When you remove it, the chemical reaction stops, and it's momentarily not working, not going through a chemical reaction. When you reconnect it into a circuit, it starts working again. There's also wet cell batteries. We're not going to get completely into wet cell batteries and how they work, but this would be like your four-wheeler battery, your car battery, these larger batteries that come in a box type situation. They contain connected plates made of different metals. So you've got all of your different metals in here. And then you've got an electrolyte liquid solution. You've probably heard that referred to as battery acid. So the battery acid is in here. And you've got a case. And this is a pullout of what those different plates look like. So you've got a positive plate, you've got a negative plate, and you've got a separator. And then you've got connectors. And so that electrolyte solution is going to activate, the chemical reaction is going to start, and those electrons are going to move from negative to positive, from negative to positive, from negative to positive, and they're going to drive that reaction. Electrical outlets provide us with a voltage difference. So batteries do provide us with a voltage difference, but the voltage difference isn't that great. You're not going to get enough voltage to drive with a car or with a simple dry cell battery. You're not going to get enough voltage. I actually tried to run the pump on my fish tank with dry cell batteries, and it wasn't enough voltage difference to run it. It ran it, but I burned the batteries up in a couple hours. So a lot of times we need a voltage difference greater than what we can find in a battery. So we're going to use electrical outlets. The average difference in the United States between the electricity that comes through our wall is 120 volts. So it's going to flow from the high here in the wall to the low, which is the whatever it is in your hand, and that difference in the United States is 120 volts. So there's 120 volts less in what you're using from the electrical outlet. That's going to drive that electric current forward and forward and forward. So when you plug it in and you pull it out, sometimes you see sparks. Those sparks you're seeing are the transfer of charges, because that's what's going on when you plug something in. Those charges are being transferred. Other countries have different outlets. They have different charges. They have, in some countries, all the outlets are round. In some countries, we do have USB chargers now. Those are a different shape. We have, this is a phone. This is some other countries. They're all different shapes. They can be different charges, and they can have different step downs in other countries. And that's why if you bring like a blow dryer from the US overseas and you try and use it, you'll burn up your blow dryer, because your blow dryer is made to work with 120 volt step down. And if you go to another country and their step down isn't 120 volts, it will either be too much energy and it will literally burn it up, or it won't be enough energy and it won't even come on. So that's they sell converters in most stores, and you can buy those converters to change the amounts of energy that are going into your appliances. That way you can use your appliances you bring overseas with you or to other countries with you and be completely fine. In the US, the only other size outlet we have besides our 120 volts are our 240 volts, and that is for our clothes dryers and our washing machines. They need more energy than your average household appliance would, so we're going to have a bigger electricity gradient there. Resistance is the tendency of a material to oppose the force of electrons, or the flow of electrons. It changes electrical energy into thermal energy and light energy. So we learned that we can't get rid of energy. It has to go somewhere. It has to be changed into something. So a resistor, which is what these little things are down here, are used to reduce the amount of energy. So as they're reducing the amount of energy, they're changing that energy. And as they're changing that energy, they're going to turn it into thermal energy and they're going to turn it into light energy. So they're going to take that extra energy and they're going to change it into thermal energy and light energy and get rid of it. We use resistors through to reduce the current through parts of circuits. A lot of times they're used in delicate machinery. If you see these green circuit boards down here, you see resistors in those a ton of times because the machinery is delicate, and if you put too much of an electric charge through it, you're going to break the machinery. So we're going to see these in computers and phones, VCRs, DVD players. Anything that has a circuit board is going to have a resistor of some kind in it to step that energy down. Which brings me, oh dear, going the wrong way. Where is my cell phone question? There it is. My question is, why does my cell phone get hot when I use it a long time? So all materials have resistance. Everything has resistance in the world. Whether it has a resistor in it or not, it has resistance. So when the flow of electrons is resisted, that energy has to go somewhere. Those electrons are still bouncing around like crazy, and that energy those electrons produce has to go somewhere. Well, it's transferred to thermal energy. So the longer you use your phone, which is a delicate piece of equipment, the more and more resistance those resistors are, the more and more energy those resistors are trying to change and trying to step down. And it's got to do something with it. So it's dissipating it as heat energy. So that's why your phone gets hotter and hotter and hotter the longer you work it or the more battery you use. It's because you're working those resistors. It's not really because of the phone. You're working the resistors, and you're causing that energy step down to occur, and it can't dissipate the heat quick enough. Last but not least is Ohm's law. So as we make wires thinner or longer or hotter, we increase the resistance. And all materials have electrical resistance, and we measure electrical resistance in something called ohms. So Ohm's law says that a current in a circuit is equal to the voltage difference divided by the resistance. So a current is equal to the voltage difference divided by resistance. So if you picture a really long wire, that's your current. You've got your little voltage difference here, so your step down here. Resistance is like pulling up on it. And it's holding it up, and it's trying to stop it from going anywhere. It's trying to slow it down. So Ohm's law says the relationship between voltage difference, current, and resistance are in a circuit, and the current in the circuit equals the voltage difference divided by the resistance. The voltage difference is how fast it's going to travel. The resistance is how much pushback we're going to get. So when we divide one of those into the other, we're going to get how much current is going to flow through that. All right, and if you need some help working some of the problems you have for homework tonight, I have another video on those.